Alright, in this video 3.2 we're going to take a look at the graphs of polynomials, which just kind of a little more of an extension of the quadratics, the parabolas, the quadratic that we just looked at. We really were focusing on all aspects of the quadratic, but this time we're going to really focus in on what we call the roots of the polynomial. So we're going to look at a couple of vocabulary words. We're going to be identifying what the word roots means and even the word the zeros. We've heard a lot about zeros, and we're going to make sure that we identify what those are. So before we get into that, let's just take a look at some arithmetic over here. We have a long division problem set up, and I'm going to use that to guide what we do over here with our polynomial long division. Okay, so it's going to be our guide basically. So so hopefully we won't be having to memorize the steps. We'll just think logically about how to do the arithmetic, and then that will guide the rest of it. Okay, so the very first thing that we do on long division with arithmetic is we don't say how many times will 1 go into 5. We actually, well, we might do that to estimate, but we say how many times will 14 go into this? Well, it won't. And then we say, well, how many times will 14 go into both the 5 and the 2, which would be 52. So we ask that question first. We go 14 into 52 because 2 digits are going to need to go into 2 digits. So I look at that, and that's about 3 times, almost 4, but not quite. So now let's think, where do I put my 3? I put my 3 right above the last digit that I divided into, right? That makes sense. I put it right there. Okay, we're going to do that process right over here. Let me get this written, set it up. We have x minus 2 that's going to be dividing into x cubed plus 2x squared minus 3x plus 1. Now, the question will be, will this not fit into that, but both of these? Will this binomial fit into the binomial? And we're not going to ask how many times. Here's what we're going to ask. We're going to ask ourselves, x, we're going to take the front runner there, and we're going to compare it to the front runner there. And we're going to say x times what equals x to the third. That's what we're going to actually say. X times what equals x to the third. In other words, we're only going to care about making the front of that binomial match the front of that temporary binomial, right? We're just taking 2 of those things, which is we can kind of think of it as a binomial. So here we go. Let's answer the question. X times what is x cubed? Well, x times x squared. So I'm going to put the x squared. Now think about it. Where did we put this one over here? We put it over the last digit. I'm going to put the x squared over the last term that I divided into, which was 2x squared. So I put that there. Now let's go back over here to the arithmetic one. I'm going to now multiply 14 times 3, right? And I'm going to put that's 42. I'm going to put it right here. Okay, so let's do that over here. Let's do that over here on the polynomials. I'm going to multiply x squared times x minus 2. In other words, I'm going to do the same process. X squared at the top times x minus 2. We did, right over here, we did 3 at the top times the 14. We wrote it underneath. Here we go. This is going to be, let's go ahead and multiply it. We're going to use the distributive. We have x cubed minus 2x squared. Okay? Now, over here in the arithmetic, we draw a line and we put a minus. So it's kind of like we've changed the sign of the 42, even though it's just our way of showing subtraction. But when we have a binomial over here, look here, we have a binomial. Here's what we're going to do. We're going to draw a line, and instead of just changing the sign of the first one, this has to be distributed, so we're going to change the signs of everything on the binomial. So here's what I say. I say draw a line, change the signs. There's a little saying you can remember. Draw a line, change the signs, plural. Okay, let's go back to the arithmetic. What do? We then subtract, or we add the column, which is 52, and negative 42 is a 10. Right? And then we bring down the next digit. Okay, let's do the exact same thing over here at the polynomials. add the column there, we get nothing. We got a positive 2x squared, and another positive 2x squared is a 4x squared. Bring down the next term. Bam. Okay, let's take a look back over here at the arithmetic. The next thing we're going to do is we're going to ask the question again. 14 goes into this? No. Does it go into this? Yes. How many times? So here we go. Back to the original question. X times what gives me, what are we going to do this time? X times what gives me this one? 4x squared. That's what we're going to ask. X times what gives me 4x squared? Well, X hold on just a second. I'm looking back at the x squared. Okay, yeah, we did that correctly. So we're going to say x times what gives me 4x squared. Here we go again. X times what gives me 4x squared. Had to double check my work. We're going to get a 4 and an x, right? Isn't that what should go in there? X times 4x should give me 4x squared. X times 4x gives me 4x squared. All right, so we're going to write, okay, this is us asking, how is this going to fit into this? So the answer is 4x, and I'm going to put it right up here. What kind of 4x? Positive, so we make it plus. So here we go. Let's multiply the 4x times the x minus 2. Use the distributive, and we get 4x squared minus 8x. Okay? So let's go back over here to the arithmetic. We said 14 goes into 106. Let's see how many times. It goes in there 7 times. So I'm going to put a 7 here. Oops, that's a 7. And I'm going to say 14 times 7. And that's going to give me 98. So I'm going to write 98 down. I'm going to draw a line to subtract. Write that. Okay. So again, let's do it over here but with the polynomial. Let's draw a line. Change the signs. Okay. And let's add the column, or in other words, let's subtract. So we've got that minus that is nothing. We've got negative 3x and then a positive 8x. That's going to give me a positive 5x. We're going to bring down the next term. Okay, let's go back to the arithmetic. What did we end up with here? We ended up with 8 right here, and there's nothing left to bring down, so we can't bring anything down there, and we're finished, right? This ends up being the remainder. And what is this up here? This is the quotient. Okay, so the same thing's going to happen over with the polynomial. Let's finish it up. We're going to ask ourselves, x times what equals 5x, right? That's the question. X times what equals 5x? That's what we're saying, x, and then that's going to try to be matched to the 5x. So the answer is 5, right? Positive 5. Since we're dividing into this 2 is going into this 2, we're going to put that 5 right above the last digit that we divided into, which is a 5. Okay, right there, that's a 5. So now we're going to go 5 times the x minus 2, and that's going to be 5x minus 10. Draw a line, change the signs. That turns that into a plus. Let's add the columns, or subtract in other words, and we get 11. So what has this found? What have we just found? We've just found the remainder. There's the remainder of 11. This right here is the quotient. All right, so not too bad. We do the same thing over and over, just like we do over here with arithmetic, we do with polynomial division. Okay, so did we find the quotient and remainder? Yes, we did. All right, let's take a look at another one. All right, so let's take a look at this one. If we want to do ordinary division on this one here, this one looks a little bit like it's missing some things, and it actually is. So I want to just use this. I don't want to work the whole problem, but I do want to use this one to remind you that when we're setting up something like this, we do have to insert the missing terms. In other words, our exponent needs to go down one at a time. Instead of jumping from 4 to nothing, we need to insert a 0x to the third. We need to also insert a 0x to the second, and we need to continue to insert, okay, for x to the first, and then of course the 3 is then the x to the 0. So when we set this one up, it's going to look like this. X to the fourth plus 0x to the third plus 0x squared plus 0x and then plus 3. So that's going to make it look a lot longer, and it's going to, we want the powers to reduce by only 1, right? So that one is understood to be 1 here, and this is understood to be x to the 0, which means it's the number 1 and we don't have to write it. Okay? So just wanted to remind you about that. And now we're going to take a look at what would happen if we had done this same problem, worked the same problem using synthetic. Okay? So with synthetic division, we don't use the x's, we just use the coefficients of each term. So we have a 1, a 2, a -3, and a 1. 1, 2, -3, and 1. So here's how we're going to do this for synthetic. A 1, a 2, a -3, and a 1. Those numbers are going to be written. We're going to leave a space right here. We're going to leave a space right here below it. And we're going to have this thing, I call it the shelf. We're going to have a number over here on the shelf. Now, what we were dividing into, that thing was x minus, that large polynomial, we were dividing x minus 2 into it, right? And so here's what we do for synthetic. We actually set that factor equal to 0, and we solve for x. And that number is the thing that's going to go on the shelf. Okay? Alright, so let's take a look at how the synthetic works. It's going to give us the same quotient, by the way, and the same remainder. So let's just make sure it does. So we're going to first bring the 1 down. That's always the first step. Bring this down. Then we're going to multiply these two together. So we're going to multiply, okay, and then we're going to place the answer right there on that line. So 1 times 2 is 2. We'll put it right here. Then we're just going to add the column. 2 and 2, 4. Now we do it again. We're going to multiply the 2 and the 4, and we're going to place it right there. 2 times 4 is 8. Put it right here. Add the column, and we're going to get a 5. So then we're going to say 2 times 5 gives me a 10. We're going to place it here. We're going to add the column, and we're going to get 11. The very last number is always my remainder. It doesn't belong to the quotient. It's just the remainder. Now, here's what we had to begin with. We had x to the third, and this was 2x squared, and this was minus 3x, and that was plus 1. That's where we got those coefficients, right? But you notice that the power of this one was a cubed. Let's look at what the quotient ended up being. The quotient was squared. We've divided out one of the x's, and so now the quotient is it's dropped 1 from the original, meaning we have 1x squared plus 4x plus 5, and that is our quotient. It's exactly what we got before, but we do have to build the x's back into it for it to actually be the official quotient for the polynomial. Okay? So, hope you can see the connection there. X squared plus 4x plus 5. It's the same exact thing. Okay, so synthetic. A lot of people like this way better than long division. It takes less time. Most people like that because of that. Alright, let's take a look at another one. So why in the world do we care about all this quotient and remainder? Let's take a look at a little more of a simplified polynomial and a divisor. So if this is my polynomial and I want to divide it by this one, I'm going to go ahead and use synthetic on this one to just kind of speed it up. So here I go. I'm going to take my divisor, set it equal to 0, and I get x is -1. So there's my -1 on the shelf, and I'm going to put my 1, my 4, and my 3 here. Let's just see if we get a remainder here, what it is. Here we go. Put that in there. We've got -1. That's going to be a 3. We've got -3. All right, my remainder ends up being a 0. Here's what that tells me. Let me go ahead and write the quotient. The quotient is 1x plus 3, right? It's just 1x to the first power. So there's my quotient. So what does this mean that we have a remainder of 0? It means that this was really a factor, right? If I say, hey, does 5 go into 20? Yes, it does. Look, my remainder is 0. That means that 5 really was a factor of 20. So that means that this really was a factor of this. If this really is a factor, it means that I've now found the quotient so that, well, let me say it this way. If I know that this is a factor, I'll say it this way. There's something called the Factor Theorem, and the Factor Theorem says this, that if this right here, okay, is a factors into this, okay, if this divides into this, then the remainder is the very same thing as us taking the x value right here, the x value, if we set that equal to 0, and dropping it in, meaning dropping in the -1 into the function. Let's take a look. This remainder is what we should get after dropping in the -1 into the actual polynomial. Here we go. That's a 1 minus 4 plus 3 is equal to 0. I get that. That's the remainder. Now, we've done a lot of function notation, and you probably didn't realize that function notation, that me dropping in a particular value, was actually me getting the remainder as if I had been doing long division. So what does that mean for me, really? What does that mean? Let me just make a quick little table. If I dump in a -1, this thing right here tells me that I'm going to get out a 0. Well, that means that this right here is a 0, okay, of the function, meaning this. It's an x-intercept. Okay, it's an x-intercept of the polynomial. So let's take a look. Let's put this back together. We've got y equals x squared plus 4x plus 3. This right here, this -1, is a 0. It's an x-intercept. Okay, it's a root. And let's look at what the other root is. Root meaning taking out the y and replacing with a 0 to find the x-intercepts, right? The roots. Okay. Well, we found the other factor is that, so let's set it equal to 0. We find that the other root is -3. So I have my two roots, two x-intercepts, which are the roots of this equation, which end up being let me say it this way, the roots of the polynomial are the zeros of the function. Okay, so the roots of the polynomial, okay, the roots, that means x is -1 and -3, okay, those are the zeros of the function. Okay, they're the x-intercepts. So if I take this one step further, I'm going to go ahead and erase this. I'm going to find my x-intercept, my x-coordinate of the vertex. I'm going to go this over 2 times 1, and it looks like that my x-coordinate of my vertex is -2. I can put -2 back in, and I'll get -1. So my vertex is at -2, -1. Boy howdy, that looks like it's really gonna confirm the rest of the information I've found, right? So there's my function. My x-intercepts, okay, my x-intercepts are actually the places, they're actually the roots of the polynomial, and they're the zeros of the function. It's all connected. Okay, this will be the last example. What if I wanted to find the x-intercepts of this polynomial function, and I don't have any place to start. I have no idea where to begin. I can't factor it, right? I cannot factor it because this is cubic. So I'm not going to be able to factor it, use the quadratic formula. I don't know how to factor it. It won't factor by grouping, nothing like that. So what I need is I need a couple of little tricks up my sleeve so that I can get started with some of the actual zeros of the function. Okay? So let's take a look at what we can do. I'm going to take this constant is going to be called P, and this right here, the leading coefficient, is going to be called the Q. Okay? The leading coefficient, meaning the first term's coefficient. Alright, what I'm going to do is I'm going to list the factors of 30, the P, and I'm going to do them this way so that I don't miss any. I just kind of start closing in on the center. So I have my 1 and 30, my 2 and 15, my 3 and 5. Those are the factors of 30. Oh, excuse me, just a second here, I just missed that. 1 and 30, 2 and 15, not 3 and 5. What in the world? 3 and 10, I missed that one, and then 5 and 6. Okay. Now the factors of 1, which are the Q, are just 1, alright? Now what I'm going to do is I'm going to find all of the rational, now that just means that they might look like fractions, the rational roots, okay, the rational roots of the polynomial, and we're going to call them the possible rational roots. Okay, so we're talking about possible rational roots, possible places where this thing crosses the x-axis, because we can't know for sure, but we can at least make a list of the possibilities. So here's what we do. We take all of the factors of the P and we set them over the factors of the Q. Well, in this case, the Q only has one factor, so this is going to make a nice easy list, and we have to consider both the positive and the negative versions of them. So here is my list: plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, 6, 10, 15, and 30. And you might be saying, Miss Savelle, you're kidding me. All of those are possibilities. Yes, they are. So here's what we're going to do. If I don't have a picture, right, I don't have a graphing calculator to help me out, I'm going to start with the positive version here, and I'm going to, the positive, a possible rational root, and I'm going to put it in synthetic, and I'm going to see if it works. I'm going to see if it ends up giving me a remainder of 0. Okay? There's 5, that's negative 6. That's going to give me negative 6, and that's definitely not a root. So I'm going to cross that one out. The next one I'm going to pick is the negative 1. You're already thinking, Miss Savelle, I'm not going through that whole list. You're not going to have to go through the whole list. Okay? But we are going to go through a few of them initially to see if we can find one that fits, that works. It gives me a remainder of 0. That's what will be the proof that it is actually a root. Okay, 1 times that's not going to be it. So I'm going to go ahead and do a few more off the clock so that we can work through this more quickly. And I'll show you what we get. So what I've done is I've just used the positive 2 and the negative 2, and look what I found. I found I found a remainder of 0. What does that tell me? That tells me that this is a root. It's an x-intercept. Now, what else does that tell me? Could I find, it says find the possible ones, right? So I listed the possible, and I'm actually taking it a step further. I'm actually now finding. Let's say that the directions are to find. So once we found the possible, those are the red ones, right? Find all the roots. What if it says to find all the roots? Well, I found one. One's negative 2. So I'm going to put that down. I got 2 of them. I got 1 of them. Now, let's take a look. How many possible roots can we have? Not rational roots, but how many roots? We could have a maximum of 3. Now, that's including imaginary and real. So let's take a look at my quotient. When my remainder is 0, let's look at my quotient. This ended up being x squared plus 2x minus 15. Can I go ahead and factor that, right? Remembering that it really is set equal to 0. If I'm going to get my x-intercepts, I'm making the y, right? This is a polynomial. The y, I'm going to make it a 0. Let's see if we can do this. Find all the roots of this thing. Okay, we got our starting point at the negative 2, and now we're going to finish up with factoring. So we're going to go plus 5, it looks like, and minus 3. Look at there. I have x plus 5 is 0, and I have x minus 3 is 0. This gives me x is negative 5, and this gives me x is 3. I've just found, they're not in order, but I've just found my 3 x-intercepts, which are the roots of the polynomial. Okie doke? Alright, so the video was kind of long, but I think we got it all, and I hope that helped. Thanks for watching.